Now then, for those of you that have seen my previous video about repairing these Xenon 8.5K bass amplifiers, you will have noticed that I was talking about a design flaw, an issue where Xenon have not optimized the power supply correctly in terms of switching frequency. And that caused the power supply FETs to run pretty hot on idle, and there was a lack of efficiency in the power supply. It drew quite a lot of idle current as well. This is bad optimization, and really they should never have left the factory like this. So what I'm going to be doing today in this video is talking you through the process of getting the power supply optimized, getting the frequency absolutely perfect as best we can on these transformers so that they run stone cold on idle and so that they can pass really good power, like the most power that's possible to pass through these transformers with these FETs to the output section to maximize the power output. To demonstrate this issue, what I've done with the power supply is I've removed all of the power supply FETs apart from just two over here, and I've also removed the rectifiers that turn the outputs from the transformers into DC that charges the caps. By removing the output rectifiers, the rectifiers here, it allows me just to run transformers individually on their own, and this just makes for simplicity. So what I've done here is I've just got one FET running the pull and one FET running the push of this transformer. So we're going to be looking at this transformer only and looking at its output on the rectifier pad here to see what it looks like and the frequency. Now, with a perfectly optimized amplifier, in this situation, in this scenario, with just the transformer powering nothing and just two FETs running the transformer, one push, one pull, there should be absolutely minimal current draw, like very low current draw from the power supply, and these FETs should run cold forever. They should never heat up. However, in its stock form, which this board is, these FETs do run warm. I will demonstrate that now. So I'm going to hit the remote on the amplifier to activate it, and let's see what she looks like. So we have the square waves there on the output of the FET. The amplifier is drawing a total of 1.16 amps, just running this pair of FETs on this transformer. If we take a look down the thermal imaging camera, you can see there already they're starting to heat up. After just a few seconds of operation, we're already at 35 degrees Celsius. Still climbing. We're now at 40 degrees Celsius. So yeah, not ideal. That was just a few seconds of operation and already they're running very hot. So why are they running hot, you may ask? We can take a look at why they run hot on the scope here. I'm going to zoom on the scope screen. Now watch this. Now this is very noisy, and the reason that this is very noisy is because this is a really terrible power supply and it doesn't filter, it's a switching power supply, it doesn't obviously filter the switching properly on the output. So ignore all the noise that you see and just try and look at the square waves here. Let's power up again. So at the start of the wave here, you've got this terrible ringing as the thing turns on, and that is due to an incorrect frequency for these transformers. So the frequency is too fast. Because the frequency is too fast, you get this ringing effect, and the ringing effect isn't resolved by the snubber circuit here. See, there's a little red capacitor and a blue resistor. That's meant to minimize the ringing, but it's so intense that that isn't actually able to sort this out. So what I'm going to do is take the probe here, and I'm going to put it on the output of the transformer so that we can see it bigger on the scope screen, turn the wave up, go and measure the frequency, and we can see what frequency it's currently running at. So the frequency that this is running at is 24.63 kilohertz on the power supply. That's quite a normal, that's actually a pretty normal frequency for the power supply to run at. So different amplifiers will optimize at different frequencies. However, due to that horrific ring there, it's quite clear that this amplifier requires a slower frequency in order to not heat the FETs up and in order to run optimally. So how on earth do we go about slowing that down? The answer is, of course, with the TL494 chip. So pretty much 99% of bass amplifiers and car amplifiers have this chip, and this chip controls and runs the power supply. It takes 12 volts from a switched remote, and it then generates out of phase square waves, push and pull on pins 9 and 10. The frequency of these square waves are determined by a couple of small components over here. If you type in TL494 into Google, it'll give you the datasheet for this chip, which tells you which pins are responsible for setting the oscillation frequency on 9 and 10. Now you can see that I've already had a bit of a mess around here, so I've just temporarily put this stock resistor back because I was playing with the frequencies. If you take your oscilloscope and you probe pin number 5, which is this one, you'll notice that there's a sawtooth wave on the screen. This is the frequency which the chip oscillates around. This is also connected to this capacitor, so this is on pin number 5. This capacitor then goes round to this resistor, which goes back to pin number 6. So pin number 6 is connected to the resistor, and pin number 5 is connected to the capacitor, and the capacitor and the resistor are connected together. This combination of capacitor and resistor value sets the oscillation frequency for the chip. So in order for us to modify the oscillation frequency simply, we just need to change the value of this resistor to either increase or decrease the speed of the oscillation. I want to talk you through a quick bit of theory as to why the speed of this oscillation is so important. So I'm going to draw the transformer here. Oh, that's a shit pen. So this is our transformer. This here is the output wind. So this is the wind that goes to the rectifiers that has the high voltage rail on it. Okay. This side has the 12 volts coming in from the vehicle. So the 12 volts comes in here and it actually goes to a center tap. So the 12 volts comes in on the middle. It then one way goes off like this and one way goes off like this. And the outputs here, these go to, if we draw our MOSFET, these go to the middle leg of the MOSFET, which is why these power supply FETs have 12 volts on them. The source of these MOSFETs is then connected to the amplifier's main ground. The gate is then connected to the TL494, one of them connected to pin 9 on one side and one of them connected to pin number 10. That means that each time the gate drive here on the gate tells the FET to turn on, this 12 volts here goes down here and gets grounded through the FET. And then when this one turns on, the same thing happens, it goes around here and gets grounded through the FET. These two, these push and pull, never turn on at the same time. So it's like a seesaw, one on, one off, one off, one on. So they're like this, they turn on and off in alternating fashion. This all happens at an incredibly high frequency, super fast. Now the next bit of explanation is not entirely accurate in terms of the physics of electrons and stuff, but I'm going to explain it in this way because it's the easiest way to understand. Imagine that you have all your electrons that are here sitting idle waiting to go on the 12 volt line. When this FET, when this gate turns on, this opens up and then these electrons then have a pathway to ground, which they will try and follow because they all want to get to ground over here. However, what happens is the electrons make it through here, get to here, but just before they can actually get to ground, this FET turns off. So then they're stuck, so then they don't actually ever make it to ground. At the exact same time, this one turns on and pulls the electrons this way, and then turns off just before they make it to ground. Then this one turns back on again. And so what you have is you have the electrons are basically going all the way through this coil here, oh fuck, all the way through this coil, oh no, all the way this way, oh no, all the way this way, oh no. So you have this kind of alternating thing where they never quite make it to ground, however they are oscillating, they're moving through the winds, therefore they create a field which is then picked up and finds its way onto the secondary wind due to how transformers work, but because this has more turns, the voltage is higher on the secondary wind than it is on the primaries. So what happens if this frequency is too slow? If it's too slow, what happens is they make their way to ground, causing a short for a brief amount of time before the FET turns off and the next one turns on. So too slow a frequency, if this turns off too late, then too much electricity goes to ground and it causes the FETs to run hot because they're basically just grounding 12 volts very quickly between FETs. If the switching frequency is too fast, however, they don't make it near enough to ground, and so they don't kind of energize or electrify enough of the wind here. They get kind of part way and then they get pulled back the other way. And that has a few interesting effects. Having a switching frequency that's too fast means that the power supply, this is an inefficient and weak transformer. It means that there won't be much current that is passed on to the output wind. And secondly, because they don't make their way through the coil completely, you get ringing occurring like from the FETs to where the electrons made it to, kind of. This is very simplified, it's not entirely accurate, but this is kind of the best way to explain it. So if it's too fast, you end up getting ringing where they didn't make it, which is why on the scope there you saw that great big thing before it actually goes to a nice square wave. That is because the switching frequency is too fast and there's a whole bunch of ringing going on the transformer. So we need to set the frequency perfect so that it's in perfect balance between here and here and here and here, so that they make their way almost to ground but not quite, and that maximizes the efficiency of this transformer, keeping the FETs running dead cool, not passing anything to ground, not causing any ringing that also heats the FETs up, and then allowing the amplifier to have as much current on tap as possible. In order to find that perfect resistance to set the perfect oscillation frequency, it's a good idea to use a potentiometer, just temporarily, that lets you work out the perfect resistance. So this is a 20k potentiometer that we found laying around at Brad's. This is from a base remote, and so I've wired some leads to it, between 0 and 20k on the wiper, and what I'm going to do is, the original resistor in here is a 24 kilo ohm. So my potentiometer is only 20 kilo ohm, therefore I can't just use a potentiometer, I need to go up higher in resistance. Higher resistance seems to give us a lower frequency on the oscillation. So what I'm going to do is I'm going to wire my potentiometer in series with this original resistor just to increase the resistance slowly to find a perfect oscillation frequency where the current draw from the power supply is lowest. Remember, if we go too slow, the current draw will start to rise up again as the electrons start to get grounded and the FET starts to just pull power to ground. So there's a kind of perfect balance point where it's just about to draw current, and then you go back a tiny bit just to where it doesn't draw current, and that's the perfect spot. So let's start at 0 on the potentiometer, which is no change, and let's start to turn it up and see the frequency change on the screen of the scope, and hopefully see the current go down on the power supply. So let's build it first. So we have 1.1 something, 1.16. So I'm going to turn it up, and we should, yes, you can see it on the scope screen. It starts to go down, and now we only have 22 kilohertz. Power supply current draw is going down. We're almost down at an amp now, 9.9, so we're down at 20 kilohertz. Let's keep going, keep going, keep going. Oh, look at that, we're down at 0.84 on the power supply. Let's keep going. Right, now we're starting to come back up again, and you see how that has cleaned right up. Wow, look at that! Yo, mate, that is perfect. This is such a sick demonstration. Right, so if I make it faster again, you see how that ringing starts to build and we are climbing on the current draw. If I just knock it down, knock it down, we're going down 7.4 amps, 7.4 amps, no sorry, 0.74 amps, not 7.4, 0.74. And now the wave looks absolutely beautiful. We see that, that is really, really, really clean. There's not much ringing on there at all, and the current draw is only 0.75 amps. If I start to go any slower, however, you see it start to build up again, the ringing gets even worse, and now we're back up at an amp again. So the perfect sweet spot is just here. 0.73 amps, and that is a wonderful looking square wave. So now what we do is we turn the amplifier off, and we take our multimeter and get it as accurate as possible. What is the resistance now across that set of series resistor and potentiometer? Once we've worked out what resistance that is, we're going to go ahead to an electronics store and buy that exact value of resistor. So this is a 35.7. So with each turn of the potentiometer, it changes like quite a lot from that. So we could get away with a 35 kilo ohm, 35.5. It depends what's available. Not every single denominator of ohm, like 0.1 of an ohm, is available. So you can either make one by seriesing or paralleling resistors together, or you can buy the closest. I think a 35 or 36 or 35.5 is going to be absolutely fine here. So just to confirm then that they do stay cold now that I've optimized the switch frequency, let's turn her on and have a look down the thermal imaging camera. So before, with a few seconds of operation, they were reaching sort of 33, 35, 40 degrees. So they're still currently sitting at 29.8. Still sitting down at 29. 30.2. Because there's only 2 FETs in there, you know, they might increase by like a tiny bit of temperature. No, look, they're 29.6 still. This is not a very good thermal imaging camera, so it might fluctuate a little bit. So they are staying, they're not moving one bit from like around 30 degrees. Yeah, they're staying right down at 30 degrees. They're not getting hot at all. It's absolutely stone cold. No heat generated by these whatsoever. Let's turn it off. And let's just feel with our hands. No, they're like colder than room temperature. They feel cold to the touch. So wow, that is fantastic. Now, because no 2 transformers will be identically the same because of just their winds, you know, they're slightly different shapes and stuff, and because these front 2 have the tiny small taps for the 12-volt regulator supply coming off them, what I'm going to do is I'm going to fit FETs in the other transformers as well, so they're all running, and I'm just going to knock the potentiometer back and forward just a touch to make sure that we have a balance between all of these transformers being happy. It might be that this one is perfect with a 35.5, this one might like a 34K, this one might like a 36K, etc. So I just want to get the perfect balance between all of them, which we can get by looking at the current output from the power supply with all of these hooked up to get the lowest number on the screen possible. 16.8 as before. We've got 3.64 amps, 3.66, 3.63. So 3.63 is the lowest, and that is 16.9 by the looks of it. It's 3.62. So pretty much bang on 17 kilohertz. Oh, gone down even further now. 3.59. 3.53 is the absolute minimum, and the frequency sits at 16.86 kilohertz. I'm just going to double check, see if that's any different from the resistance I read earlier. 35.6, so no, it's pretty much exactly the same. So a 35.5 will be absolutely bang on, and that will get this working optimum efficiency. So I'll now go ahead and order those resistors and also the rest of the MOSFETs for this amplifier, so we can get this Xenon 8K back up and running fully in the heatsink, and then also the other one over there, we're going to put, that's fully functional, all the parts are on that one, so it just needs to go back in the heatsink, and then we'll have 2 amplifiers ready to play. I hope you enjoy this little demonstration for the power supply optimization and the switching frequency, and I hope that you learned something from it. Until next time, take it easy.